I want to welcome you to our new schedule, our new weekly schedule. This will be the only video lesson of the week. This will be the only lesson of the week. And when we get to the end, I'm going to give you 3 assignments to choose from, and you pick one. And all you have to do is get that one done, turn it into me, and that will be credit for the entire week. So I hope that takes a little bit of pressure off and maybe makes this whole situation a little bit more manageable. I do want to encourage you, if you haven't already, to find and at least download, if not print off, the formula sheet for this unit. It's on the website, and I sent you a link Monday morning with that will take you to the page where you can download that, but I also attached it in the email. There's a whole lot of formulas in there, and it might be a little bit overwhelming at first, but we'll slowly work through them, and you'll see a few of them today. I'm thinking we might get about 4 of them today, and then we'll start adding a couple more each week. So let's get to it. I'm going to switch over to the whiteboard, and let's dive into this. So the one thing I want you to rethink back on is when you watch me create those cross sections. I did it with a banana, and I did it with a stick of butter, star fruit even. But most of them relevant to today is I want you to think about the cranberry. So I took the cranberry out of the can. It came from a can like this, but obviously it was not grilled chicken soup. It looks delicious. It wasn't this soup, but it came from a can like this. And when you take the cranberry out, it comes out looking literally like a can, like a cylinder. And when I sliced it, I sliced off kind of the top of it and created this circle of cranberry, a delicious circle of cranberry, as I recall. But I want you to imagine for a second that instead of being a so thick circle, it was tiny, 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 tiny thick, like just a flat ring. So basically no height, just a circle. We can think we've done circles before, but it's not a big deal. So imagine you have just a circle of cranberry, and you put it on the table, and you take another circle of cranberry, put it on top, another one, another one, and then you eventually stack it all up. That's what a cylinder of cranberry starts to look like. So instead of looking like that, it looks something like this, like that. And what we have is we have all of these little mini circles of cranberry stacked up in there. And so the first thing I want to sort of look at today is how we calculate the volume of a cylinder. So it could be a cylinder of cranberry, or it could be a cylinder of, like this soup right here. Now, obviously, this soup is going to be very difficult to take circles out of because it's a liquid. But the way I want you to think about this is by looking at a single one of these circles, finding the area of that circle, and then just stacking them up. So quickly, when we thought back to like 2-dimensional objects, we'll start with like a rectangle. We would say area equals base times height, right? The base here and the height goes right there. And that was sort of a 2-dimensional way of describing this. What we're going to do here is we're going to change that focus to area equals a different kind of base times the height. And by the different base, what I mean is this entire circle is a base. And so I need to find the area of that circle. I can do that. Area of circle is pi times r squared, pi r squared. And then we have this height, h, And this becomes our first formula. The area, excuse me, what am I doing here? Guys, gals, what is going on? This is volume. Volume is going to be the area of a circle times the height. So we've got volume equals pi r squared, circle times height. So I want to do a quick example here. This, I measured this soup right here. It has a height of 5 inches. And it has a diameter, notice I said diameter, not radius, of 3 inches. So how much soup is in here? It says 18.6 ounces, but that's a weight. I want to know volume. So let's walk through how we would do this problem. We know that the volume of this cylinder is going to be pi times, now we need r squared. If the diameter is 3 inches, what's the radius going to be? 1.5 inches? So it's 1.5 squared, pi r squared times, times h, which is 5. And we'll get my handy calculator out here. Pi times 1.5 squared times 5 is 35.34. Now let's think about units here. I'm measuring in inches, but I'm not talking about area, which would be square inches. I'm talking about volume, which is cubic inches. And to be clear, as you go through and do some of these, and I know we're not going to be doing a whole lot of these, it's possible sometimes that you will see this written, change colors so you can see it, including pi as part of the answer. So we just calculate this, it's 11.25. So both of these are valid answers for the volume of this can. So that's how much soup I have, about 35 cubic inches of soup. And this is probably going to be my lunch today. So that's a cylinder, but there's another three-dimensional object I want you to consider, and that is a prism. Now, a prism doesn't necessarily have to look like a box. It's one of the more common forms of prisms, but what we really need to make a prism is some sort of polygon on the bottom that we can then sort of pull up and extend up into 3 dimensions. So in this case, I've got a rectangular base, and then that rectangular base has been lifted or pulled vertically to create this 3-dimensional object. We'll talk about this more in a second, but I want to go back. I want to show you a couple of pictures of other prisms so you get an idea of what we're talking about here. This right here is the Toblerone candy, and you'll notice that the way it's sitting, it's not really on a base. The base here, remember, the base is the shape that you have to pull up and it has to look exactly the same on top as it does on the bottom. In this case, it's just a line on the top, so that's not the way it goes. But if you flip it up on end, then the base of the Toblerone candy would be a triangle. And then if you pulled it all the way up, at the very top, you'd also have a triangle. So we call this a triangular prism. Now, this is one you're probably a little bit more familiar with, Rubik's Cube. And this will be what we call a square prism, because no matter what face you put it on, the base of the prism is a square. And then when you pull it up and make it 3-dimensional, the top is a square as well. This is not necessarily a square prism because we have a rectangle on the bottom. So it's a rectangular prism, and that's why it has this odd shape to it. And then there's something that you might have seen before, maybe you had before because it's delicious, this hot cocoa, abuelita. They're great, but look at the shape of the box. That's why I love it. It's a hexagonal prism. the base of this box is a hexagon. And then when you pull it up, make it three-dimensional, the top is also a hexagon. And now next time you look at that, you're always going to see that as a hexagonal prism right here. Yeah. Okay, so let's go back and let's figure out how volume works in a prism. And this is a little bit tougher to draw, but I'm going to see if I can do it reasonably well here. Draw that as a solid line. I try to draw solid lines as lines that we can see. And then there's going to be this one here that we actually can't see. So there's some in the back that are kind of a problem as well. So let's talk about volume. Volume of a prism requires us to think about this as if we had a flat square or rectangle, whatever you want to call it, on the bottom. And then we just put stacks and stacks and stacks. So just like we stacked up these circles of cranberry in my example before, we can stack up these flat sheets. And I got a great example for you. Remember this? This is the same. This is my same calendar, what I send out every morning. But look at this. It's made up of these pages, right? So if you look at this from the side, you'll see that this calendar is just a stack of individual pages. So this is how a volume of a container, of a prism, can be thought of as a stack of flat sheets. Well, the area of the flat sheet, we're going to call B. That's this area right here. This is B. And then we're going to, so we have the area of that sheet, then we're going to stack it up a certain height. It becomes base times height. But again, it's the area of a base times the height. So it gets a little bit tricky because, if I can go back here, in this example, I'd have to be able to find the area of a hexagon, which we haven't really done this year, but we have to do that. Rubik's Cube, okay, I can find the area of a square pretty reasonably, and probably I can find the area of a triangle decently. It looks like it's a equilateral, equiangular triangle, which means I'm guessing this is probably going to be like 30, 60, 90, a short side, half the hypotenuse, that kind of thing. So it can be done, but what I want to do is I want to show you how to do it specifically with my almond, sweet, and salty nut granola bars. So I have some measurements here that I took of this. The base of this is, so this is this one here, and it's again, it's drawn kind of funky, right? But we'll just make do. This is 6 inches by 1.5 inches. So 6 inches long, 1.5 inches wide, and then the height is 5.5 inches. So what does the volume look like here? Well, if you figure this out, you might see this is, you know, length times width times height. So length times width times height. And that's a pretty common way of calculating volume of a rectangular prism. Why? Because the area of the base is a rectangle. So we have 1.5 times 6 times 5.5. And we'll do a little calculation. I know 1.5 times 6 is 9, but 1.5 times 6 times 5.5, and we get 49.5 cubic inches. That's how much space is inside here. Now, I'm going to ask you a couple of questions as we get through this lesson, because is that how much granola is in here? No, because if I open this up, you will see that, like, the space is not fully used, right? I mean, it's pretty close, but it's not, this is not filled with granola bar like the cranberry is filled, or like this can is filled with soup. So this is more like how much space is inside here, not so much how much granola bar, because you can see there are some empty spaces. Okay, So that's great for volume, but there's more to it than volume. And this is where it gets into a little bit of a marketing conversation, a little bit about how business works. And I want to take you down this road because this could be something that you end up dealing with at some point in your life, whether you're working for a manufacturer, a marketer, and so on. And the question becomes not so much how much soup am I going to put in here, because the soup certainly costs money, but you realize that this is the Safeway signature, they got to make these cans too. And these cans cost money. Like this tin can costs money to make. And you know, we just do, we open this up, dump it out, we throw this away, or we recycle it. But the can costs money. This box, this cardboard costs money to make. And basically, it's got no use to the customer. I mean, I want what's inside. I don't really want the box. So we start to ask ourselves, well, why a cylinder? Why this? And I'm going to give you a little bit of insight before we get into the calculations. These package really, really nicely. I can stick these on a shelf, side by side by side by side, and I can stick them in a box, and this will fit tight inside a box. This is a really great, efficient use of space. This, on the other hand, is not. If I put another can next to it, think about if you've ever seen like a case of soda or something. If you open it up, there's all this space in between because cylinders don't fit together very nicely. There's all this extra space. So why make a cylinder? So there's two things here. One is, you know, the actual can that the soup goes in. The next thing is the manufacturer's got to make, you know, 48 of these, put it in a big box in a case, and ship them out to all the stores. So not only are they making the soup, they've got to pay for the cans that the soup goes in, then they got to pay for the boxes that the cans of the soup go into to ship out to the stores. So why make a circle when there's all this empty space? If you look on the shelf, you'll see that there's empty space in there. They don't fit together like these do. You may have an idea why we use cylinders and not boxes for soup. Like, why doesn't the soup come in this box right here? And the answer generally is because of the way my hand works. See how nice it is to hold my hand? I can put this in my hand, pull off the top, I can pour it very nicely. It's not as easy to pour a box of granola bars. So you'll notice that soda, water, soup, things that we want to hold in our hands and pour are often cylinders. Whereas things that we just need to stack, like boxes of cereal, boxes of pasta, any kind of thing comes in a box, I guess, is typically packaged like a box, because this is not the vehicle we use for delivering it. We open it up and we take out what's inside. Okay, so let's take a look at how surface area works. Because surface area is literally the area of the surface. That is some great teaching right there. I tell you what, that is gold. You guys are lucky to have me as a teacher. Surface area is the area of the surface. I never would have probably figured that out. But what I mean is, it's how much stuff it takes to make the can. Now, what I want you to notice here is this can has an interesting shape. On the bottom is a circle. On the top is a circle. So I know for sure that I have two circles. I mean, the company has to make two circles to make this work. And then they've got this can. And I don't know how big this can is, but I got a little secret here. This label covers the can, right? So if I go through here, let me see if I can get through like this. Oh no, I can't get it open. Well, I'm just gonna fake it best I can. You thought that was instruction gold. This is just money right here. Okay, so what I have here is I've got a label that effectively covers this can. if I peel this label off, look what shape I'm going to get. Torn things notwithstanding, I get more or less a rectangle. See that? A rectangle, here's a can, wrapped around the can. When I peel it off, it looks just like a rectangle. So what we can start to do, I'll pick up my mess here, is we can draw something called a net. And a net is a two-dimensional figure that depicts everything that goes into making this cylindrical can. So for example, for this can, I know there's going to be a rectangle. And then also attached to each side of the rectangle is a circle. See that? That's a net for this cylinder, which means if I could curl up that rectangle into a can shape, a cylinder shape, then I could fold the top circle down, fold the bottom circle up, and I would have this shape right here. See that? So this net indicates to me the dimensions of the surface area, or how much can they have to make. And we know from before some of these measurements, this was 3 inches. And how big was how tall was my can? 5 inches tall. So this was 5 inches, right? Because remember, the length of this rectangle we don't know yet, but it wraps around, and the height is 5 inches. So I have 2 circles that are 3 inches in diameter, and then I have this rectangle. So my surface area is going to be, watch this carefully, 2 circles plus 1 rectangle. Okay? And let's see what the area of the circles are. Well, the area of a circle is pi r squared. So this is going to be 2 pi r squared. And now this rectangle is a bit of an issue. So I know the height, it's got to be length times width, right? Or base times height. So I know the height of it, but what is this length? Well, this length, watch carefully, this length wraps around the entire can, yeah? It wraps around the entire can, so this distance right here has to be the circumference of this circle. There's the height, but it wraps around a distance of this circle. So this is going to be 2 pi r. So we have a base of 2 pi r and a height of h. And this is the surface area of a cylinder. Now, your book doesn't have this, so you make sure you write this down. This is one of your formulas on the sheet, but this is like a bonus topic because your book doesn't cover this. So the surface area of any cylinder is 2 circles and 1 rectangle, 2 pi r times h. And we won't take the time to do this, but you can do it. You have all the numbers in here. Remember, the radius is 1.5 inches. You can certainly figure that out. Okay? All right, last thing today is, again, surface area, but this time of a prism. And specifically, it's going to be rectangular. So what I'm going to do here is I'm going to take this box, I'm going to open it all the way up. Okay? And I'll get all the stuff out of here. And I want to show you what this makes. Now it's a little bit tricky because some of the stuff is repeated, right? So let's think about this. There is a top, long skinny rectangle, going to look like, let me change colors. It's going to look like this. There's also a bottom, long skinny rectangle. Yeah. There is a vertical side that is not quite as tall and skinny. It might look like this. And there's one on either side of that. And then there's these big faces that look more or less square. So it's going to look like this and like this. Okay, so again, see how there's duplications here? These two sides duplicate. So I'm going to tear this side off, do a little surgery right now. So I make sure I've got that top covered. The front and back are both covered. The bottom's covered. There's just a little bit of duplication here because these sides overlapped. And here, we haven't fun yet. And this, and this. Now, what I have is a box that's fully formed. See that? It's all complete. But when I open it up, I get a net. And I want you to see what's in here. The lighting is a little bit tricky here, but I want you to see this. I've got two big, we'll call square parts. That's, whoops. That is those two, the big square parts. I have this bottom section right here that matches this top section here. That was these two. And then I have these two side flaps that go here. And again, the manufacturers of these granola bars have to decide how much cardboard do I want to put in here. I don't want to waste cardboard because literally people open up and they're just going to throw this away. I will recycle this, but this is not useful other than to deliver the product to me, and then it's not useful anymore. So they don't want to spend any more than they have to, but they have to spend something. So what does this look like? Well, if you think about a three-dimensional shape here, let's see if I can draw this appropriately. And you notice I'm drawing this a little bit less square-like and more, it's almost like it's sitting this way now instead of up. But we've got this, you know, length, width, height. So what we've got is, like in this case, the big bases, this is length times width. So surface area is going to be 2 LWs, 1, 2. And then we've got, you know, maybe width here and height here. So it's going to be 2 width times heights, 1, 2. And then we've got length and, well, height, plus 2 LH, 1, 2. This, guys, is not a very exciting formula, but I think it's almost easier just to take it apart. If you have any sort of three-dimensional prism, you just have to deal with 6 faces, right? Find the area of 6 sides. Go back and look at this. This Rubik's Cube, 6 faces, right? And so if you found the area of one of the faces, you can very easily just find the next one, and the next one, the next one, and once you get 6 of them, you're done. Now, in this case, they're all the same. In this case, they're not the same. But there's 2 big faces, 2 top and bottom, and then left and right, and you can find the area that way. So I know this kind of seems like a lot of work, but I think this is valuable stuff. I think it's worth knowing how volume is calculated and how surface area is calculated as well. So here is the plan for the week. You have 3 assignments from which to choose. They are option 1, page 476, 6 through 12, 16 to 21. Option 2. This is going to be a CUDA worksheet on surface area. Option 3 is going to be CUDA on volume. You do not have to do all 3. I just want you to do one. If you want stick with the book, stick with the book, and you're good to go. If you really like surface area, do surface area. Eventually, I'm going to test you on all this stuff, but only one is required. All the rest is just for your own sake. We're not going to do extra credit here. I'm just gonna keep this really simple. But if you have extra time, you can do extra practice. The CUDA worksheets have answers. I'll put some answers up for the book page in the next day or so. So with that, I will bid you a good week. We'll see you next Monday.